GameSide.com. GameSide.com.
Howdy, partners! Ready to learn some logic gates? And, or, and not? The basic building blocks of a CPU are the and, or, and not logic gates. Put enough of them together in the right order, boom, a CPU. An and is all true to be true. An or logic gate is all false to be false. And a not flips true to false or false to true. Take enough of these, put them in the right order, and you've got a CPU. Much like Lego bricks, simple basic pieces, put enough of them together in the right order, and boom, you've got a Lego building. The simple tiny pieces that make up a circuit are not much different than the simple tiny pieces that make up a Lego building. Truth tables. For a given input, what is the output? For the AND truth table and the AND logic circuit, all true to be true. The only time the AND is true is when all the inputs are true. When all the inputs are true, the result is true. If any input is false, the output of the AND gate is false. The OR is all false to be false. The only time an OR gate is false is when both inputs are false. If there's a single true on the input, the output, F, is going to be true. Not, flip true to false, false to true. If the input to a NOT gate is true, then you'll flip it to false. If the input of a NOT gate is false, you'll flip it to true. Truth tables. Focus on that last column. That is the output of the gate. This red box is the output of the AND gate. When both inputs are true, it outputs true. If any input is false, it outputs a false. Look at the output of the OR gate. If any input is true, the output is true, and it's only false when they're both false. Look at the output of the gate. That is the result of the gate. In logic and computer science courses, we often use true and false to determine the output. But with digital logic, the output of a gate is 1 or 0. So with 1 as true and 0 as false, let's look at this the way digital logic would look at it. In the truth table, focus on the last column. AND means both inputs must be true, or 1, for the output to be true. 1 is the equivalent of true. If both A and B are true, then the result, F, is true, or 1. And if any of the inputs are false, if any of the inputs are 0, then the output of the AND logic gate is a 0. Mom says she'll buy you a video game if you clean your room and wash the car. When either of those is false, no game for you. If you forget to wash the car, Mom's not getting you that video game. Focusing on the last column, OR means either input can be true, or 1, for the output to be true, or 1. Dad says he'll buy you a video game if you clean your room or wash the car. When both are false, that's when you don't get the game. Dad's a little easier than Mom. All you have to do is one of the chores and you'll get your video game. But if you do neither, the output of the OR is 0 or false. Again, focus on the last column. Not means flip a true or 1 input to a false or 0 output. Flip a false or 0 input to a true/1 output. It's important to know these truth tables for AND, OR, and NOT, forward and backwards. A NOT truth table turns a 1 to a 0 and a 0 to a 1. Memorize these 3 truth tables. It's very, very important. Below are 4 possibilities when adding 2 binary digits with no carry. Logic gates can build circuits to implement this task. You could add more gates to handle the carry, more gates to do a 16-bit add, more gates to build an entire CPU. We know from binary addition, 0 plus 0 returns a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. 1 plus 1 is 0 with a carry of the 1, which we're not going to focus on just yet. But we can use logic gates to implement this type of circuit. Back to our Lego example. The bricks themselves are very, very simple components, but when arranged in large numbers, can create buildings, and with more Lego, entire cities. And, or, and not gates are simple components, but when you arrange them in large numbers, can create binary adders, and with more gates, ALUs. The important thing is to memorize the truth tables. Know them forwards and backwards. Logic gates. NAND, NOR, and XOR or exclusive OR. This is the NAND gate. It means not AND. If you feed the output of an AND gate directly into a NOT gate, you create a NAND gate or not AND. This is a NOR gate or not OR. If you feed the output of an OR gate directly into a NOT gate, you create a NOR gate or not OR. This is an XOR gate or exclusive OR gate. Create a gate that is true when only one of the inputs is true, false otherwise. These are three new logic gates. Last slide we learned AND, OR, and NOT. This slide we'll learn NAND, NOR, and exclusive OR. Here's some truth tables for these logic gates. These are not really new gates. They can be made from the AND, OR, and NOT gates. But in digital design, they are used so often they are manufactured as individual gates. This is the not AND gate, or NAND. This is the not OR gate, or NOR. And this is the XOR gate, or exclusive OR gate. With truth tables, it's important to look closely at the outputs of the gate. The output of the not AND is the opposite of the AND gate. The opposite of the not OR gate is the opposite of the OR gate. That's kind of a duh. The NAND gate is false wherever the AND gate would be true, and true wherever the AND gate would be false. The NOR gate is false wherever the OR gate would be true, and true wherever the OR gate would be false. With the exclusive OR gate, you're only true when the inputs are different. Compare the output of the NAND gate to the AND gate, and you can see it's the exact opposite of the same inputs. After all, this is the not AND gate. Created a new column in red here, just temporarily to show you what AND would do with the exact same inputs. With both inputs as true, AND would of course produce a true result. So not AND of course would produce the opposite, or false. With the inputs being 1 and 0, the AND gate would produce a 0. Therefore not AND would produce a 1. And everywhere the AND gate produces a 0, the not AND, or NAND gate, produces a 1. It's the exact opposite of the AND gate. That's what not AND means. Let's compare the output for the NOR gate to the OR gate, and you can see it's the exact opposite for the same inputs. Once again in red, I put the output of what the OR gate would be for the same inputs. With two inputs of 1, the OR gate of course would output a 1. So the not OR gate outputs a 0. With two false inputs, the OR gate would output a 0. So the not OR, or NOR gate, outputs a 1. Wherever the OR gate outputs a 1, the not OR gate outputs a 0. Wherever the OR gate outputs a 0, the not OR, or NOR gate, outputs a 1. Not OR. The small o on the graphic means not. If you look at that little circle at the end of the graphic, see the circle there? See the circle there? That's what makes this a NAND gate or a NOR gate. That little circle means take the not. This is a normal OR gate with a not at the end, which makes it a NOR gate. This is a normal AND gate with a not on the end, which makes it a NAND gate. The truth table for the exclusive OR. Notice the big X here and the big OR there. This is the XOR gate, exclusive OR. The English word exclusive means limited, a small number. Exclusive means only one input can be true. Different inputs is true. The same inputs is false. Exclusive OR means only one of these inputs can be 1, and the gate will output a 1. If the inputs are the same, this gate outputs a 0. If the inputs are the same, this gate outputs a 0. Exclusive means only one of the inputs can be true for the gate to output a 1. Look, computers are really simple. All they do is move some ones and zeros from RAM to CPU. They then manipulate or change the ones and zeros in the CPU, then move ones and zeros from the CPU back to RAM. Logic gates perform all three of these tasks. We can use NAND gates or NOR gates or exclusive OR gates to do all three of these items. That's what logic gates do for a computer. They move and manipulate ones and zeros. Logic gates are the core of how a computer works. Does a Java or C++ programmer need to know how a CPU works? Yeah. How good is an auto mechanic without knowing how engines really work? Not very good. How good a brain surgeon without knowing how the heart and lungs work? Not very good. How good is a computer programmer without knowing how a CPU works? Not very good. You need to understand the inner workings of the computer to fully understand the software that you plan to program. Boolean algebra, invented by English mathematician George Boole. He wrote The Laws of Thought in 1854, where he explained Boolean algebra. It is the algebra of true and false, used in the analysis and design of digital circuits. Kind of interesting, seeing how he wrote it 100 years before computers were invented. More efficient than drawing circuits of AND, OR, and NOT gates. It's just another way to express logic. It's another way to show true-false logic. The same way a circuit can represent an AND gate, there is a Boolean algebra expression for AND. The same way a gate can show an OR, there is a Boolean algebra expression for OR. Just like there is a logic gate for showing NOT, there is a Boolean expression for NOT. Boolean expressions. Boolean AND can be expressed as AB equals F or A and B equals F. The variables AB can only contain the values true/1 or false/0, and of course F will contain the 1 or 0 result per the AND truth table. While Boole himself used a dot to indicate AND, on today's keyboards you will sometimes see A star B or A asterisk B. Without an operator, AB right next to each other is assumed to be A and B. Here is the logic gate for the AND. Here is the Boolean expressions for AND. Boolean OR, A or B equals F. It looks like numeric addition, but with Boolean algebra, read this as A or B. The variables AB only contain the values true/1 or false/0, and F contains the 1 or 0 result per the OR truth table. Boolean OR, or the plus sign, has lower precedence than the AND, and in a mixed expression, do the AND operations before the OR. Boolean NOT, A with a bar over it equals F. The NOT operation is a bar over the expression you wish to NOT. The variable A only contains the value true/1 or false/0, and F contains the opposite per the NOT truth table. The overhead bar is difficult on today's keyboards, so I often use minus A equals F as not A equals F. Let's compare the and the or and Boolean precedence. And before or. Do the B and C first. In an expression that mixes an or with an and operation, the and has higher precedence. A or B and C. If you mix an or and an and in the same circuit, you must do the and first. Notice how I drew this circuit. The B and C occurs first, and then the output of the and gets fed into the or, and the or is done last. Use the parentheses to do the or first. This expression, parentheses A or B, end of the parentheses, and C, parentheses have higher precedence than and. In this situation, we do the or first. Drawing the circuit, we will or A and B first and feed the output of that into the and with C. You can see that Boolean expressions can represent circuits of logic gates. For large circuits, Boolean algebra is sometimes better. It is easier to look at a complex Boolean algebra expression and simplify it than it is to look at a complex circuit diagram. Do you see the reason behind Boolean algebra? This is a lot easier to express than drawing circuits. This is a lot easier to express than drawing this circuit. When we get into larger circuits, it's a profound difference between expressing it as a Boolean algebra expression or drawing a very big circuit. There are Boolean expressions that represent any digital circuit, and they are easier to write and optimize than drawing regular circuits. Here's a Boolean NAND. This is a Boolean algebra expression for the NAND gate. There's a drawing of the NAND gate. This is the Boolean algebra. A or B and not the result, that's Boolean NOR. And there's the NOR gate. Boolean exclusive OR. There is the symbol for exclusive OR in Boolean algebra. This is read as A exclusive OR B equals F. There is the circuit for that exclusive OR gate. Any circuit can be expressed as a Boolean expression. Any Boolean expression can be shown as a digital circuit. Boolean algebra is an efficient way to analyze and design binary circuits. Quite often, it is easier to deal with a circuit as a Boolean algebra expression, much easier than drawing the diagram. What would any algebra be without a set of identities, rules, and laws to help simplify expressions? Boolean algebra is no different. We need to learn a bunch of identities, rules, and laws to help simplify Boolean expressions. Boolean laws or rules help simplify Boolean expressions. We're going to learn a set of identities and rules or laws to help us simplify expressions. Looking at this expression, 1 and A equals A. If A starts as 0, the result will be 0. If A starts as 1, the result will be 1. 0 or A equals A. Once again, if A is 0, the result is 0. If A is 1, the result is 1. This is called an identity. And when you simplify a Boolean expression like that, you can substitute A for the expression. This is called the inverse element. True and false is false, and vice versa. False and true has to be false. True or false has to be true. False or true has to be true. These are the inverse elements. Again, we're just doing simple substitution here. 0 and false is false. 0 and anything has to be false. True/1 or anything has to be true. If you already know one side of the OR is true, it really doesn't matter what this is, the result has to be true. True and true is got to be true. False and false has to be false. If A starts out as true, the result of this expression has to be true. If A starts as false, the result of this expression has to be false. Same thing with the OR. If A starts as true, the result has to be true. If A starts as false, the result has to be false. These are identities, and they help us simplify Boolean algebra expressions. Boolean algebra is sometimes like normal algebra. This is the commutative law. A and B equals B and A. A or B equals B or A. They have to be the same. Now, when I say it's sometimes like normal algebra, 3 times 4 is the same thing as 4 times 3. 5 plus 6 equals 6 plus 5. Just like in normal algebra, we use these laws to simplify Boolean algebra expressions. This is the distributive laws. A times parentheses B or C is equal to parentheses A and B or parentheses A and C. A or parentheses B and C is equal to parentheses A or B and parentheses A or C. That's the distributive law. Let's be careful. Not all Boolean algebra works exactly like normal algebra, but still, we're moving terms to simplify expressions. But in this case, the Boolean algebra expressions are circuits. So when we simplify a Boolean algebra expression, we are simplifying the circuit and using less gates to build that circuit. Associative laws. A and parentheses B and C is equal to parentheses A and B and C. A or parentheses B or C is equal to A or B in parentheses or C. These are the associative laws. Associative and other laws are about moving terms. When you move terms, you can form identities. Identities can then be simplified. Once again, the whole purpose of learning Boolean algebra is to be able to simplify Boolean algebra expressions. When you simplify Boolean algebra expressions, you are simplifying the circuits you'll need to represent that expression. De Morgan's theorem. The thing I look at when I see De Morgan's theorem is it's really creating an AND gate from an OR and 2 NOT gates. What? It's creating a NAND gate from an OR and 2 NOT gates. This is a NAND gate. I can build it using an OR and 2 NOT gates. This is a NOR gate. I can build a NOR gate from using an AND and 2 NOT gates. Interesting. De Morgan's theorem not only allows you or helps you simplify Boolean algebra expressions, it's also very similar to the NAND and NOR gates. To go in a little more details, a NAND gate is A and B, not the result. That can be simplified with De Morgan's theorem to not A or not B. Well, here's the circuit diagram for a NAND gate. Here's the result of De Morgan's theorem, and this circuit uses 2 NOT gates and a single OR. Here's De Morgan's NOR gate. A or B, not the whole result, equals not A and not B. Here is the logic gate for NOR, and here is the De Morgan's version of the NOR, not A, not B, fed into an AND gate. That little line right there is attached. Truth tables. Circuit drawings of logic gates and Boolean algebra are the first 2 ways we've learned to design digital circuits. The completion on the circuit design trinity, the third leg of the circuit analysis stool, is the truth table. This is an example of a truth table. A truth table with 2 inputs, A and B. Here's the result of A and B. That is a truth table. Here's the result of A or B. That's the truth table for A or B. And here is the result for not A. A truth table is also a way to design a digital circuit. This is called a 1-bit adder. It has 2 inputs and a carry in. It could have 2 outputs, a sum and a carry out. Well, here, for these 3 possible inputs, these are what the 2 outputs should be. For these 3 possible inputs, this is what the output should be. A truth table is a way to design a circuit. You specify for these inputs, I want those outputs. Boolean terms. The truth table to the left describes a 1-bit adder. A and B are the input bits, C is the carry-in bit, and the sum is the output. Focus on the lines that output the sum of 1. There's a 1, a 1, a 1, and a 1. They are the lines with the odd numbers of 1s on the input. We will look at the carry out bit soon. Please do not worry about that just now. We're going to add 2 binary bits together and with a carry bit determine what the sum should be. Boolean terms. Look closely at the first line with the sum of 1. I've highlighted it with the red box. A is 0, B is 0, and C is 1. The Boolean term for that input, read out loud, is not A and not B and C. On a computer keyboard, it may be -A and -B and C, or simply not A and not B, C. Looking closely at the second line with the sum of 1, I've highlighted it with the red box. A is 0, B is 1, C is 0. The Boolean term for that input, read out loud, is not A and B and not C. And on a computer keyboard, it may be typed out like this, or simply not A, B, not C. Looking at the third line with the sum of 1, A is 1, B is 0, C is 0. The Boolean term for that input, read out loud, is A and not B and not C. Computer keyboards don't do these vertical bars very well. So on a keyboard, I usually use a minus sign in front of the term. The fourth line with the sum of 1, A is 1, B is 1, C is 1, produces a 1 in the output or sum. The Boolean term for that input, read out loud, is A and B and C. On a computer keyboard, you may type it out like this, or simply ABC. These are the Boolean terms for each line in the truth table that produces a 1 in the sum output. To create a 1-bit adder circuit for the sum product, you would need to OR these terms together. The circuit would be fairly large, so a little Boolean algebra to simplify the circuit, or a technique from a future lesson, Carnot maps, would be used to create a smaller circuit. But basically, if it's this input, or that input, or that input, or that input, we should output a 1 for the sum. Boolean terms. The truth table to the left describes a 1-bit adder. A and B are the input bits. C is the carry in bit, and C out is the output carry out. Focus on the lines that output a C out of 1. Here, 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 and here. They are the lines with 2 or 3 ones on the input. The full circuit has 3 inputs and 2 outputs, sum and C out. Showing just one output at a time here, it's easier to break down this problem with one output at a time. We'll look at both on a future slide. The Boolean terms, look closely at the first line of C out that produces a 1. A is 0, B is 1, C is 1. The Boolean term for that input read out loud is not A and B and C. On a computer keyboard, it may be typed out like this. Looking at the second line, where C out produces a 1. A is 1, B is 0, C is 1. The Boolean term for that input, read out loud, is A and not B and C. On a computer keyboard, it may be typed out this way. Looking at the third line, where C out produces a 1, C out has an output of 1. Looking at the input on that line, A is 1, B is 1, C is 0. The Boolean term for that line of the truth table, read out loud, A and B and not C. On a computer keyboard, it may be typed out this way. Finally, look at the fourth line where C out produces a 1. This is the fourth line of the truth table where C out produces a 1. A is 1, B is 1, C is 1, or A is true, B is true, C is true. The Boolean term for that input read out loud is A and B and C. On a computer keyboard, we might use the asterisk or the star operator. To create a 1-bit adder circuit for the C out output, you would need to OR these terms together. The circuit would be fairly large, so a little Boolean algebra to simplify the circuit would be used to create a smaller circuit. Combine it with the sum circuit and you have a full 1-bit adder. You put 32 of those together and what do you get? A circuit that will add two 32-bit binary numbers together. Looking at the truth table, if it has this input, or that input, or that input, or that input, we should output a 1 for the circuit. The digital trinity. Are you designing or analyzing digital circuits? You can do one of three things. Number 1, draw a circuit diagram. Number 2, write a Boolean algebra equation. Number 3, create a truth table. Often, it's a combination of all three. Create the full truth table to the left, use Boolean algebra to simplify the terms, then draw the resulting smaller circuit. This is the full circuit we've been looking at. For these three possible inputs, this is what I want to output for the sum. This is what I want to output for the carry. I'll build this truth table. I will reduce the circuits using Boolean algebra and draw the resulting circuit, which tells me the logic gates I need to build to create a 1-bit adder. NAND/NOR circuits. Recall the Lego analogy. If you were building a 15,000-piece sculpture, what would be easier? One created from 15,000 pieces of the same Lego brick, or one created from 5,000 red, 5,000 blue, and 5,000 yellow bricks? I think building a sculpture out of 15,000 of the same piece is easier than building a sculpture out of multiple different pieces. When building a 1.5 million gate computer chip, what is easy? One built from 1.5 million of the same logic gate, or one built with 500,000 AND gates and 500,000 OR gates and 500,000 NOT gates? Millions of the same gate is far easier to build. What NAND and NOR circuits allow us to do is build our entire circuit out of the same logic gate. Rather than having to juggle multiple different types of logic gates, NAND and NOR circuits allow us to build more simplified circuits out of the same gate. The AND, OR, and NOT gates are the basic components all digital circuits are created from. They are also the Boolean algebra operators. However, the NAND and the NOR gates have an interesting property. All three basic gates, AND, OR, and NOT, can be created using circuits built from a single gate type. Entire chips can be created from one type of gate. You can build an entire CPU out of just NAND gates. Or you can build an entire graphics processor of only NOR gates. If you mix a bunch of different gates, AND, OR, and NOT on the same chip, It's hard to build. If you use one of the same gate, NAND or NOR, it's a lot easier to build a circuit. What we're going to do here is we're going to learn how to build these three different gates, AND, OR, and NOT. Build all three of these gates from simply NAND gates. We'll use one type of gate, a NAND gate, and build all three of the other gates, AND, OR, and NOT. Here is a NOT gate created from a NAND circuit. If I tie the inputs together, then the output of the NAND gate is basically a NOT gate. Think about it. When A is 0, both inputs would be 0. The AND would produce a 0. Then NOT AND would create a 1. That is the input I have shown on this circuit. But if I flip it and set the input to 1, the output would be 0. If these were both 1s, this would be a 1. NOT 1 would be a 0. That is the NOT truth table. If I wire a NAND gate this way, it basically functions as a NOT gate. This is a NOT gate built out of an NAND gate. Look at the red boxes. I'm going to build out of two NAND gates an AND gate. This is an AND gate created from a NAND circuit. If I put two 1s on the input, the AND would produce a 1. The NOT AND would create two 0s on this input. Two 0s on this input would produce a 0, and NOT 0 produces a 1. This circuit of NAND gates produces this truth table. And guess what this truth table is? This is the AND truth table. Once again, I've only shown one set of inputs. When there's an input on A and B, boom, this is what the circuit works out to at the end. Two 1s on the input produces a 1 on the output, which is exactly what you want an AND gate to do. This is an AND gate built entirely of NAND gates. Let's now build an OR gate out of nothing but AND gates. I'm going to build a circuit using only NAND gates, and it's going to implement an OR gate. The OR gate created from a NAND circuit looks like this. With three NAND gates, I can build an OR gate. Focus on this line of the OR truth table. It says if A is 0 and B is 1, I should output F a 1. This is definitely the OR truth table. Let's trace this out. This line of the truth table says 0 on the A input. A 0 on the A input would produce a 0 for the AND and a 1 for the NOT AND. There'd be a 1 on this input. A 1 for input B would produce a 1 on the AND and a 0 on the NOT AND. So I'll end up putting a 1 and a 0 into this final NAND gate. That produces a 0 on the AND, but a 1 on the NOT AND. So with 0 and 1 as the input, this circuit outputs a 1. With a 0 and 1 on the input, this circuit outputs a 1. And for all these four possible inputs, this circuit will output this specific output. This circuit will output a 1, 1, 1, 0. This is OR gate built out of three NAND gates. Now let's not leave NOR out of the game here. You can also build all three of the basic logic gates out of only NOR gates. Once again, we're going to use one type of gate, NOR, and only NOR, and we'll build a NOT gate out of it, an OR gate out of it, and an AND gate out of it. This is the NOT gate created from a NOR circuit. When A is 0, the output of this circuit will be 1. When A is 1, the output of this circuit will be 0. This is the example I've shown above. A as the input. That puts two 1s as the input of this OR gate. An OR gate with two 1s on the input is a 1, but not OR would produce a 0. The 1 just flipped to a 0, and that's what a NOT gate should do. If I put two 0s on the input here, this would be a 0, and the NOT 0 would be a 1. That is the not truth table. This circuit produces a NOT gate. The goal here is to build entire circuits out of nothing but NOR gates. Here's an example of building an OR gate out of nothing but NOR gates. Our OR gate created from a NOR circuit. I'm going to put two NOR gates together and tie them up this way and produce the output that an OR gate would create. This circuit implements the OR truth table. I'll show this last case with two zeros on the input. An OR gate should produce a 0. Well, let's trace this circuit. With two zeros on the input, OR those together, you get a 0. NOR them and they become 1s. With two 1s on the input, this OR gate produces a 1. NOR that and it becomes an output of 0. Two zeros on the input outputs a 0 on the circuit. That is the case we showed. And for every possible input, A and B, it will produce the same output as an OR gate. What we just did is we built an OR gate out of nothing but NOR gates. Finally, in order to build a digital circuit, we need AND gates. Let's build an AND gate out of nothing but NOR gates. The AND gate created from a NOR circuit looks like this. It takes 3 NOR gates to build an AND gate. Here is the truth table for the AND gate. For these inputs, those are the outputs that an AND gate should produce. This is the AND truth table. Let's look at this specific input. A is 1, B is 0, should produce a 0 on the output. That is an AND gate. A is 1, B is 0. With an A as a 1 on this input, the OR part of the circuit will produce a 1. The NOR will make it a 0. With 0 on this input, the OR part of this circuit will produce a 0. The NOR will make it a 1. My inputs at this level are 0 and 1. 0 or 1 is 1, but NOR that and it becomes a 0. For the input of A equal 1 and B equal to 0, this circuit does absolutely produce a 0. If you were to trace all 4 inputs on this circuit, these 4 inputs would produce the exact same output F. That is an AND gate built from nothing but NOR gates. We still do the design using AND, OR, and NOT gates. They are not going anywhere. But computer chips are made by machine. You download the simplest design of AND, OR, and NOT gates, tell it to manufacture with all NAND gates or all NOR gates, and it will create a chip using just one gate. It comes down to simplicity. We are starting to put billions of logic gates on one chip. Do you want those billions of logic gates to be all one logic gate? Or do you want them to be a mixture of many different logic gates? It is much easier, cheaper, and faster to manufacture a complex computer chip using the same logic gate. That's what NAND and NOR gates do for us. They allow us to build entire circuits out of a single logic gate.
Ginside.com